the last video, I have explained you the total energy associated with each and every orbit of an atom. What was the equation? Minus 13.6 into z square divided by h square. These many electron volts. This is the total energy associated, right? So when we substituted the value of Z-1, that is for hydrogen atom, for first, second and third and fourth orbits, we got the values like this: minus 13.6 electron volt for the first orbit, then this one, then this one, then again minus. So all this minus represents that electrons are bound to the nucleus. Now what we are going to do, we are going to take hydrogen gas in a cylinder. It's a transparent cylinder. Okay. Now from here, from one place, it's a container. From one place, we are allowing white light to pass through this container. So it's a hydrogen tank, transparent hydrogen tank. What we are going to do, we are going to allow white light to pass. So what we are expecting the same white color, the same white light to be received at this end. So let's say we have a specimen in this way, hydrogen gas, white light in, it has to be white light out. But I mean, how many colors do white light have? It has violet, indigo, blue, green, yellow, orange, red. So how can we see these colors differently? Through dispersion. If we can do the dispersion with a prism. So with a prism, when we do dispersion, we can see violet light has been split light has been split into violet, indigo, blue, green, yellow, orange and red. So if this is white light, but with the experiment, what we have seen that from here the output, that is the white light coming out from the container, when we have allowed to pass through a prism, we have seen certain colorations missing. For example, blue and yellow. All other colors are there in the white light spectrum. So let's say the spectrum represent as this thing. So we have all the colors from 4000 angstrom, that is low wavelength violet, till 8000 angstrom, that is red. So let's say this is a spectra. All colors are there in between. So blue will come somewhere in between. So all waves with different wavelengths are there in the white light. So this was the input. Here we have fed this thing. But in the output, what we have seen, from that spectra, certain color is missing. So this will be represented as dark band. From the white light, these many are missing. And what is the reason for these missing colors? Bohr was able to give an explanation for this. Why it has happened? Because the electron has got excited from lower energy level to higher energy level. I will explain it to you. So now this electron is at an energy level of minus 13.6 electron volt. Now inside this orbit, it cannot undergo any kind of radiation. Okay, within this, it cannot accept energy, and after accepting energy, it can't be in the same orbit, and at the same time, it cannot also emit energy and be in the same orbit. Inside the orbit, the energy has to be constant. That is for sure, according to Bohr, because energy is associated with different orbits. So radiation from a particular orbit is not allowed. Radiation outward, radiation won't be emitted outside, and even radiation cannot be accepted by the electron and be in the same orbit. But what they can do is, whenever they are able to get some radiation, able to get some wave, it can accept energy and jump into another orbit. The problem is it can't be in this orbit after accepting energy, because after accepting energy, it will be a new value. So with an orbit, it can only be one energy. Now after accepting energy, if the energy value is this much, then it can easily jump to the other orbit. Now, how radiation is associated with energy? We know that energy associated with a photon. Photon is nothing but an electromagnetic wave. So electromagnetic waves are nothing but photon carrying energy. Now, energy associated with a wave, with a radiation is nothing but h nu. where h is Planck's constant and nu is frequency. So different frequency is associated with different energy. Frequency can also be written as c by lambda. So E is equal to hc by lambda. Now the one which is in the case of violet, substitute 4000 here, you will get the value of energy. So violet is having higher energy and red is having lower energy because wavelength is higher with red. So what will happen whenever the radiation, whenever we allow white light to pass, out of white light, this electron will accept certain frequencies or certain wavelength. I can call it as frequency or wavelength because frequency is equal to c by lambda. So frequency is equal to a constant, c is velocity of light divided by wavelength. So anyway, frequency is a property of a wave. I can also describe wavelength as a property of wave. I can use either frequency or wavelength. Anyway, it is connected by this equation. Now, from the all wavelength, that is from 4000 till 8000, this one is white light. Some of the waves are accepted. Which are those waves? Whenever they accept those waves, these electrons can easily go from one position to another position. Not only from 1 to 2, it can also go from 1 to 3. It can also go from 1 to 4. So these energies, these radiations will be accepted by the electrons and it will undergo excitation. These are called as excitation. The one which is when electrons are here in the first orbit, those are ground state. From ground state, it will go to an excited state. How it has accepted energy, how it has got the energy from the incoming radiation. So let's say it is having all the frequency. Out of that, how much energy is required to jump from first orbit to second orbit? First orbit is associated with energy minus 13.6. Second is minus 3.4. So how much should I add? Here in this case, I should add minus 10.2. Now, when an electron at the first orbit take an energy of minus 10.2, plus 10.2, minus 13.6 will become minus 3.4. So it can only accept the radiation which is having an energy of 10.2, not only 10.2. So that is 10.2 is in between 1 and 2 transition. That is from ground state to second orbit. Now, if it is for the third orbit, then you can see the difference in between minus 13.6 and minus 1.5. Now, for the fourth orbit, you can take the difference in between minus 13.6 and minus 0.85. So, only specific, discrete wavelength will be missing. That is the reason for this kind of spectra. Now, when they are accepting an energy, let's say this is 4000, right? Angstrom, 8000 angstrom. So, let's say by accepting this frequency, it was able to jump from 1 to 2. But in between these frequencies, whenever they accept energy, it can't exactly reach here. Let's say in between these two, if we are providing 5 electron volts, what will happen? Minus 13.6 plus 5. That will become approximately, exactly 8.6. But there is no orbit associated with an energy of 8.6. So it won't undergo any kind of excitation. So that kind of radiation will never be accepted. Only those radiations, only those waves, only those colored the frequencies that has got an energy and that is capable of taking it exactly from here till here, those will be accepted. Now, when those are accepted, that will be absent in the outcoming radiation, the outcoming white light. So, from 7 colors, some of the colors will be missing. These colors has given energy to electron and that has undergone excitation. Other colors, if they are accepting, that can go to an orbit, but that orbit is not existing there. So, that won't be accepted. These are absorption spectra. We are giving a light, out of that something is missing. This was the white light we have given. We had all the wavelengths and out of that some wavelengths are missing. So, accepting this wavelength, it has undergo an excitation. This one, another excitation. This one, another excitation. Clear? Now, in the next video, we will see emission spectra. Here it is absorption spectra where it undergo a transition from ground state to excited state. Now, in emission spectra, from excited state to ground state. Thank you.